electrons will be heated, and that energy will be dissipated in the ionosphere. So let's see how your theory, what your theory predicts as far as the ionosphere is concerned, and is that relevant is ionospheric observations.
I have not taken the thing beyond this point. I mean, one would have to find out, take a model, say, where this dissipation takes place in the magnetosphere, find out what the gradients of pressure are there, see what the magnetospheric currents are, find the divergence of these to get the parallel current, see where they enter the ionosphere, take into account the resistivity to calculate the electric field, and then calculate heating and so on. That's you know.
That's still down the line.
My word.
I think Carl McElwain had a comment which was apropos to some of the previous discussion, perhaps also that question.
Yes, first I have a question. Is it your starting thesis that there is a penetration of the solar wind plasma into closed field lines of the magnetosphere?
Yes.
Okay. Now, it is also the case that when you go to compute the character of this, that only a certain selected trajectories can make it.
Right.
That means that it only fills a part of the phase space available to particles on these closed field lines. Now, as we know that these are not empty field lines, but have a pre-existing plasma on them from some other origin, either old solar wind particles, which presumably have changed their character by this time, or particles from the ionosphere. But I just want to point out, therefore, these two plasmas, the old plasma and the new entering plasma, are going to have very different characters. And so it would look like this beginning thesis is subject to experimental test, is to ask, are there two plasmas occupying two parts of the available phase space?
Do you know of any such
I think
experiments?
before the conference is over, we'll see that the answer is yes.
Do you have a comment in response to that?
Very good.
Very good. I think Jules Fayer had a comment. Jules, the microphone.
A small one in connection with, who was it? I think, was it Akira Hasegawa, who mentioned that there is a charge separation problem as these protons enter, but wouldn't that be a less severe one in the steady state? In other words, one need not imagine that, I mean, if these protons enter continuously, then it wouldn't be a sudden charge separation arising as it would be otherwise.
Well, actually, I'm saying that steady state is impossible. So
I see.
Wait, pardon me, could we have a microphone there? Start over again.
Actually, my comment is related with either this steady state is possible or not. In fact, it might lead to a situation where the steady state solution is impossible because you have a continuous accumulation of charge, and that the electric field is continuously changing in time.
I see. So one would have to calculate the electric fields that are needed and the currents and so on, and this has not been done by Keith Coles. Yeah, okay.
Are there any, there are several members of the audience who have worked quite extensively. Am I coming on the microphone, or do I need to stand closer? That have worked extensively on these models. I feel we're straying a bit from the topic of the conference, which is the coupling between the outer magnetosphere and the ionosphere, in the sense that we're really looking at just the source mechanism, which is driving a very elaborate set of currents and other phenomena. But are there any other people who wish to make comments on these theoretical questions? As I see what's happening in the session now, we'll probably have a coffee. We'll perhaps continue theoretical discussions of the source generator, and perhaps a few more comments having to do with the field-aligned currents, which is the obvious direction to pursue your talk. Perhaps have coffee in 10 or 15 minutes, and then reconvene after a short coffee break to hear Ron Burrows. So I think at this time it's worth talking about both the continuing discussion of the theoretical mechanism of the generator and some of the consequences of the field-aligned currents. I guess my immediate question to Keith, since no one is obviously jumping up, at this point, is that the observations of currents, admittedly very intense currents in the auroral zone, always show them to be in conjugate pairs rather than single large current sheets coming down into the ionosphere. Now this is going to impinge a bit on what Ron Burrows has to say, so we have to be very careful. But so from a theoretical point of view...
You mean to both hemispheres at once?
Yes, to both hemispheres.
Well,
But they seem to occur in downgoing and upgoing pairs rather than one big ingoing, one big outgoing.
oh, well, such pairs, I would imagine, would occur at that stage when you randomize the velocity of the flow and produce this bubble, if you like, of hot electron gas. Now, in the simplest case, if one considers a cylindrical bubble enveloped by the magnetic field with the gradient of pressure radially, oh no, that will give us circular currents and nothing to the ionosphere. One has to have a different geometry, but in any case, you must have, since this is your generator, you must have currents to and from that. I mean, there's no way out of that, I think.
But on the same side, I mean, on the morning side, I think the observation is that it's, although the poleward current in the northern hemisphere seems to be a bit stronger at times than the outward current on the same side, morning side. In fact, they're just about the same. It isn't a large inward current on the morning side.
Oh, I see. On that question, I seem to favour the idea that is being pushed particularly by Sugiura, that the two poleward currents are more connected with each other than the ones across the auroral zone. That one has equality of the polewardmost current on the dawn side with that on the dusk side over the polar caps, and that the currents at the lower L values are probably related to trapped plasma, which is generating plasma which has been convected inwards by the electric field and energized, and producing currents by a gradient of pressure, which then give you the currents in the correct direction on the dawn and dusk side, but at a lower latitude. And it's not entirely clear in my mind that and of course these two current systems will interact. I mean, we need to learn how they interact, and you know, it's not entirely clear to me that they are coupled directly. They will certainly be coupled somehow, because I mean, the same electric field is driving the whole system.
Vitinis, microphone, please.
Well, I'd like to try to isolate, I think, some of the questions raised in this talk, which I think are really related to the topic. The topic of this conference, and those which are not. That if you look at the basic predictions of your model, I think a number of those, such as the fact that solvent plasma enters into the magnetosphere at a certain fraction and it carries some energy and transfers momentum, and gives rise to current system, which is basically into the dawn side and out to the dusk side. And so I think essentially are common to a great variety of theories in the outer magnetosphere, which differ quite widely in some cases in their basic assumptions and approximations, but agree on those particular conclusions. So while it's a very interesting topic to pursue, I think it's a little bit sort of out of place in this conference, and there are other conferences devoted essentially to this topic. The main prediction, which is a specific thing dealing with interaction, which you have made, is a remark that the existence of kilometric radiation would give rise to resistivity, which will profoundly modify the convection pattern associated currents. So that's a feedback essentially from the ionosphere back into the magnetosphere. And again, that general feature, I think, is sort of common to a variety of theories, although in this case you do have a specific mechanism which can perhaps be tested. The remark is that something which happens in the ionosphere will severely disrupt flow in the outer magnetosphere, which, as I understand, is your basic notion. In your particular case, this would be a development of resistivity due to production of intense radiation by some unspecified process. I think there are many other, perhaps more reasonable possibilities, such as modification of convection by anospheric resistivity. But I think it is that aspect which perhaps ought to concentrate on here and not the details of particle entry, which I think really belong to another conference.
You have a response to that? You're hooked up.
Well, I considered it appropriate myself to introduce these things because one must consider the generator in this whole problem, and it's part of the generator to consider the entry. The question of resistivity, interaction with the business, these things have been considered in the past. I thought it was appropriate to consider a new possibility in this regard, so that's my excuse for that.
Dr. Kremigas?
I'd like to comment on the question of field-aligned currents that Peter Banks brought up, namely that you indicated that on the morning side or on the evening side you end up with current seeds on the same side. And that's indeed the case when you have so-called events, precipitation events going on. But in the steady state case, which is I believe what Keith was referring to, there is indeed a net flow inward on the morning side and then outward on the evening side, and that is now very well documented by the results of the triad magnetometer data. I'm not sure whether you're familiar with that, Keith, but I know that in one of your slides where you have the reversal in the early afternoon side, which is at about 1500, and that's one of the observational facts that have come out of the triad magnetometer data, that the reversal in the flow does seem to occur at about 1500 local time. And I was wondering whether you have looked at the published data from triad so far to see how consistent your picture is with the observations.
I'm afraid I just don't understand what reversal of what flow. I haven't caught this point.
The boundary between the downward flowing currents and the upward flowing current. There is a distinct discontinuity in the data at about 1500 local time in the steady state case, which has been observed from the triad data, and I believe has been discussed by Potemra, Nijima, and Sugiura.
Yeah, yeah, the reversal in the direction of the currents you're referring to. Okay. No, I wasn't aware of that, but this seems to be, well, in a sense, I mean, this goes back to Fairfield, for example. Fairfield had such a reversed currents, and Sugiura had them as well in his model, I believe.
These are observed.
They're observed, yes, they're observed, right. And these, I mean, and they are present in many theories, I believe, as well.
Could I ask a question? Is the discussion audible to everyone in the audience in the rear? Yes, Jules Fair.
One more question. You haven't really talked about the Earth's rotation. Do you have any opinions on the importance of that? I sort of, 12 years ago, thought it might be important, and I don't think anybody has talked too much about it since.
No, I'm always intrigued by that one too myself, Dr. Fayer, and I would like to spend a lot of time thinking about it, but I wouldn't care to bat that question right now. It has relevance, of course, to the asymmetry of the SD current system, and the Axford-Hines type theory, for example, suggests that the Earth's rotation explains that. There may be other possibilities for swinging the current system round. In fact, I think so to answer your question specifically, I haven't considered that in this context, but it's related to that problem. And if I could just get onto that problem for a minute and make a comment, I think we ought to realize that the current systems are tremendously variable in the polar regions, and this average current system, which appears to be skewed around, is only an average. And any theory that is proposed has to explain tremendous amount of variability in electric fields and currents in the polar regions.
I've lost track of the microphone. Joe Dupnik.
Can I show 2 slides, Peter? Or should I wait a little later for the slides? Yes, they are. First. With reference to the field-aligned current problem. Okay. The problem is, how do the field-aligned currents that the 2 sheets
close. And we would all like to think that there's an upper poleward sheet system that closes across the polar cap and an equator system that's somehow connected to things further in the magnetosphere. And what I'd like to say here is that there's a triad pass in the evening sector, Chattanooga, about 1830 local time. The magnetic field perturbation from triad satellite is shown here, and Chattanooga is up here at this point. The magnetic field vectors, perturbation vectors, are along the oval. And we can compare the currents that would require this, would produce this magnetic perturbation, which are transverse to this, with the kind of currents that flow in the ionosphere of Chattanooga. And we're seeing essentially an inward current system here and an outward current system here on the triad satellite. Chattanooga finds that there is indeed a current that is flowing. Where is our current? Our current is flowing along this way, and there is a component of motion which is going upwards across the oval. This is one example. Electric field is transverse to the oval. The point here is, if I can go on to the last slide. Do you have it? Yes, fine. The point is that as we watch the oval move over a period of a few minutes, these two currents of Chattanooga match fairly well the current that we need to close the field-aligned current sheets entirely within the ionosphere. In other words, the current system flows basically from the equator edge in the evening sector toward the poleward edge and then out again, rather than having...
Two currents.
Excuse me?
What do you mean by two currents?
I1
and I2.
There is a time... Thanks for that. It's very simple, Andy. There was a small time change in the measurements, and this is a few minutes before and a few minutes after the triad satellite pass. These are the two times of Chattanooga, and the triad pass is right in the middle of those things. Even as the oval changes is the point that what we find is that the current system encloses essentially from the inside part, the lower latitude part, closes to the outside, the high latitude part of the current system, and not at least very closely, not necessarily having two independent systems. I think this is a major problem. I'm not sure I really like this at this stage, but this is the indications that we have. I don't know if they've been
How frequent is that occurring? I mean, is it a rare event or what?
We don't have that many triad passes. All the ones that we do have indicate that the current closure is at least within a factor of 2 from the equatorward to poleward and poleward to equatorward side, depending on local time. There are imbalances, as has been pointed out by the triad satellite, but they seem to be very strongly coupled with the inside, the low latitude current systems, much more strongly than we might normally suspect.
I'd like to try to avoid more discussion of this particular aspect because Ron Burrows has more to say, and I think we should wait for his comprehensive tutorial before we really go into great detail. So I would like to call for anybody who has a slide or a discussion relating to the theoretical aspects of the generator or things that are going on inside the magnetosphere. Dave, do you have something on that?
Yeah, I'd just like to ask Keith if within his model he can give us any indication of what should be the carriers of the field line currents in these high latitude regions.
Of course, that's a difficult question. Many people have considered what they should be, depending upon different configurations of electric fields and so on. I mean, Rasbach... I'm lost myself, Andy, on this. I say this is a very difficult question. There are some people who believe that ionospheric ions must be the carriers when there are significant parallel electric fields. If there is enough plasma along the field lines, well, it depends upon the background plasma density. I think if there's plenty of plasma available, then I think it's reasonable to expect electrons to be the carriers of current parallel to the magnetic field. But if there's a scarcity of plasma, then according to the analysis of some people, it appears that ionospheric ions have to be the carriers. So I think depending upon the situation. I don't know, what's your answer?
Well, you're saying your theory is going to be able to go either way, I guess.
Depending upon the amount of background plasma. I think this is a crucial thing in the whole of this discussion of field-aligned currents. What is the pre-existing background plasma all along the line of force? Central problem.
If consider abundant and not abundant, then where do you draw that line?
I have no idea. I have no idea. I'm sorry, but other people could answer this question better than I.
The question was from Ted Fritz. What did Keith consider abundant and non-abundant? And
I don't know the answer. Somebody else may.
We're getting a bit pressed for time, and I think Tom Hill has a comment or a question on that.
Yeah, we have a couple of slides to show relating to the particle injection mechanism.
Leave the microphone there and come stand up.
Yeah, this is a two-part comment. I have 2 slides and Pat has 3. Yeah, we've been looking at some AEC particle data from the Lee particle detector to try to see if we can distinguish 2 mechanisms of solar wind particle injection at the cusp. Here I've illustrated the first injection mechanism that we tried to look at, and that is through magnetic merging at the nose of the magnetopause. You have a pointer? And what I'm trying to illustrate here is that if merging occurs, if injection occurs through merging at the nose, one expects a velocity dispersion of cusp particles because you're combining a parallel velocity, which brings the particles from the injection point down to the satellite at low altitudes, with an E over B convection velocity towards the pole. This velocity is the same for all the particles, and this velocity depends on the energy, so that as a result of this, one expects the highest energy particles to appear first down at low altitudes, and the progressively lower energy particles to appear at progressively higher latitudes. The next slide shows the other injection mechanism that we've looked at, namely particle diffusion across field lines in the cusp. Now, I should point out that the stationary particle trajectory kind of injection that Keith talked about generally brings particles across the magnetopause only by a few gyro radii, at least on the day side. And the observations of the latitudinal width of the cusp show that the injection mechanism somehow has to transport particles very efficiently across the field lines. The latitudinal width of the cusp is several thousand or tens of thousands of gyro radii at the least. So diffusion would be the other possible way that we've looked at of getting particles across field lines and spreading the cusp in latitude. And tried to illustrate here that if the diffusion random walk step size is proportional to the particle gyro radius, then one expects that a diffusive injection should result in an opposite kind of velocity dispersion. Here, if you look on the poleward side of the cusp, you should see the highest energy particles penetrating most deeply onto the poleward side of the cusp, the open field line region. Pat's now going to talk about some observations that relate to the distinction between these 2 mechanisms.
Well, the nice thing about having 2 different kinds of injection mechanisms is that we looked for them and actually found both of them. The first slide. Keep it down because it's the next slide. Okay. This shows the merging type dispersion that was his first case. The highest energy protons arrive first, followed by the lower energy protons. The model gives a specific 1 over lambda squared. This fits this 1 over lambda squared to an excellent degree. I have a slide which he won't let me show that resolves what the source spectrum was that produced the velocity dispersion, and it's very exciting because it shows that these are not, the source is not pure proton magnetosheath spectrum, but an accelerated proton magnetosheath spectrum. Someone wants to ask me a question, and I can show you, sneak in the slide later. The next slide is just, now here is the lower cusp boundary occurred just before this slide, and this next slide is backwards in time. The spectrogram that just preceded this one in time. Next slide? No. The next slide. excuse me, not the previous slide, the previous time. The next slide. Great. Now, this is very difficult to see. In fact, it's virtually impossible to see. But here's the lower cusp boundary where the trapped electron population died off. Here's the very beginning of the highest energy protons coming in from the cusp. And very, very faintly, you can see in this area, you're going to have to focus that a little more, I think. Yeah, that's better. Very faintly now we can see these protons entering in. And we see it goes from fairly low energy protons to very high energy protons. Again, this diffusive model that Tom was just speaking of, the highest energy particles are able to penetrate the most, and this is several degrees of invariant latitude at an altitude of about 1,200 kilometers. So we're talking about a very efficient mechanism to diffuse in particles. We fit this with a numerical model of that Tom was just saying, and we're getting extremely rapid diffusion here of the order of a part of a gyro radius per gyro period. And interestingly enough, you can even see it in the electrons. The highest energy electrons, of course, are outer zone, but these medium energy electrons also show a diffusive character in that the lowest energy stuff diffuses in first and the highest energy comes in further.
What are the energies of those electrons?
The diffusive electrons here?
Yes.
These are around a kilovolt. These are outer zone at 10 kilovolts, and secondaries at, less than a kilovolt. But the diffusive particles are around a kilovolt.
Two brief questions. If you have a question, we need a microphone.
Could you tell me what the scale in minutes is along the bottom there?
Yes. That's a nice thing about the Lie is that has a good sensitivity. This is 1 minute. We get a full spectrum every second.
Okay, so what I'm going to say is that if it's 1 minute between the time the notations of numbers, which one can't read, then probably that represents about a 5-degree width of penetration. Is that right? Because
no,
it would travel about 2.5 degrees a minute, would it?
Well, you can read this is about 2. Yeah, it's about 2 degrees a minute. That's right.
Okay, so it is about 4 degrees. Okay. Yeah. Well, my second question then is, would you like to show your other slide?
Sure, love to. Last slide. This is what we've taken the fact that the fastest ones arrive first and the slowest ones arrive next, and we've deconvolved the original source spectrum for the protons that we saw in the cusp. And interestingly enough, this is not magnetosheath. If you say that's magnetosheath velocity, your temperature is way too high. In other words, we suspect that this is stagnated flow that had a big temperature that's been merging, has given it an alpha phase velocity, field line velocity that's come down. When we fit it to the lambda, 1 over lambda squared, to find out the dispersion, we have onboard convection velocity measurements. Rod Helis gave us the measurements. We were able to find the field line distance to the injection point. It turned out to be very close to 20 RE. So it's all very self-consistent. This is coming in from the nose. It's more energetic than magnetosheath stuff is at the nose. Tanis, you come?
Yes, I'm always puzzled when someone speaks of the magnetosheath spectrum.
That's true.
In fact, the magnetosheath temperature can vary from essentially equal to solvent velocity down to the solvent temperature.
That's true.
And so I can only speak of magnetosheath spectrum at a specified location.
That's right.
Then I have to say how one gets it, from the Spider's models or from what? And what I use in your case when you say it's not a magnetosheath.
Okay. Well, if you look at Spider's model, if you look at Rosenbauer's polar magnetosheath data, you either get flow velocities of a couple hundred to 300 to 400 kilometers per second, say at the polar cusp, but a temperature of only like 100 eV. And you look at proton data, and a temperature of 100 eV at a flow velocity of 300 or 400 kilometers per second is about what is typical at the polar cusp for the proton data.
Yes, but the velocity expected to be proportional to solvent velocity.
That's true.
Not variable a factor of 2 from time to time.
That's true. That's true.
So basically, you're comparing the Mach number then.
I have never seen, and I've looked at many months of magnetosheath data. I've never seen a temperature that high and a flow velocity that high in the magnetosheath anywhere.
So you also understand the flow velocity can be almost anything depending what it's doing in the solar wind. So the only thing one has to look for is the Mach number. And on the Mach number in the magnetosheath varies from 0 at the nose and down to solar wind value far downstream.
That's true.
So you can always find a place in the magnetosheath which would correspond to the Mach number you're seeing here. The only question is, where is that place? Is it at the nose, or is it at 10 degrees away, or 30 degrees away, or what? And that's the only question you can really pose in this case.
Going to let Tom.
Yeah, go ahead, Nancy.
He'll need a microphone.
Well, it'll take a minute to answer the question. The Mach number here is of the order of 2. I think it's between 2 and 2.5. And you can't find that kind of Mach number in the magnetosheath according to the usual flow calculations unless you go considerably behind the cusp. The Mach number near the cusp is more like between 1 and 1.5. So we're looking at plasma that had to come in the usual flow model either from behind the cusp, which is very hard to understand how it got turned around and came back towards the Earth, or else plasma from near the nose that has been accelerated through some process other than the usual expansion of the flow. And this is the point that we're making.
Yeah, the point is we were following, like I said, we used this 1 over lambda squared dependence to take the field-aligned distance where these particles came in. And according to that model, in a very simple convection model, this plasma came from the nose, where it should be stagnated. And it is not stagnated.
One more question, I think, then we'll break for coffee. Is there a microphone on this side?
Does this really mean then that the total energy per particle that one is talking about here adds up to more than what you would expect? In other words, there has been some energy input to this particular class of particles. It might be worth mentioning in that respect that there is a Chapman-Farrow current necessary to flow around the bow of the magnetosphere in order to give you your discontinuity in field, and there may be an electric field around the bow of the magnetosphere as well, and the dissipation of energy represented by the E dot J could be going into these particles. Now, whether there's enough of them to take all the energy and so on is an interesting question. I expect even Walter might have a comment on that.
Well, anticipating that, we, by several ways, estimated the total energy input that these particles would give to the ionosphere. And if you assume that these particles came from a, say, 10 RE by 1 RE cross-section at the nose, you get around 10 to the 10th watts, which is a nice number. You can also get that same number by looking at what the loss cone would be at the nose, and and what the observed latitudinal. This is not, but I must qualify that this is an exceptional case. We did not have very many southward magnetic fields during the time period that we were looking at. These two, this one and another one, were the most southerly ones we had, and we had a very short injection that was strong. Most of the time, the injection is not this strong. During the times that we saw. Now, presumably, during more southerly magnetic fields, it might be even stronger, but it was just the satellite was not seeing too many.
The pressure seemed to be to get on into experimental data. I know for sure Tom Holzer must have a theoretical question, and it'll be the last theoretical question before we break for coffee.
Well, it's a comment, really. I'm wondering if maybe I've missed something in not thinking about this for about a year, but I used to think that the cusp mapped into the nose as well as into regions up on the flanks of the magnetosphere. So I just don't understand what people are saying when they say there's a Mach of 1 at the cusp. That doesn't mean anything. I mean, we're thinking of pictures of the cusp, which go out into a certain region, but that isn't true if you look at the mapping. It maps into a very large region on the magneto. Perhaps it maps into the entire magnetopause. So I really wish we could get things straight about where the cusp maps, because I think that's very confusing in this whole discussion.
What I meant was the magnetosheath just above the cusp, well into the magnetosheath, but if you take the magnetopause and dot it across where that cusp comes in, the magnetosheath flow above the cusp is around Mach 1. But I agree with you that the cusp itself probably maps down to the magnetopause in the front and the magnetopause on the rear as well. And in that case, I think that the source would map down to a stagnation